Supposed to write an insertion sorty dealy flippy thingy-majiggy?
Yeah.
Okay. Big money.
I mean, I like Sean White, but I would have preferred to see that the guy from Japan who was like 17 win, because Chloe Kim.
Didn't he get second?
Yeah, he came in second, but Chloe Kim was also 17 and she won the women's half pipe.
So you
the one the first medal for USA was 17.
Yeah.
He also overslept and almost lost his jacket. Dropped the F-bomb on like.
But
Yeah.
but Sean White had to his last run. He had to beat that guy.
Yeah.
So I mean, he had to under pressure.
I still would have liked to see.
So I was hoping that he was either going to do what he did and have a really good run and win, or like just crash horrifically, like to the point where like he wasn't going to be able to even like receive his medal. You know, like I had to have a proxy come in to get them. I mean, I don't want anybody to die. Okay, but hospitalized for a week and then full recovery, I'm good with. Full recovery, it'll be fine. This is all being recorded, so I want to make sure I cover my bases. You remember that sometime when you're like reading my manifesto or something. I'm too lazy to write a manifesto, I think. All right, so we're supposed to. I think we actually filled an array last time, right? So let's gut some of this. All right, so we created an integer array. What's this little asterisk thing? What's that syntax for? It's a pointer. All right, so we create an integer array. What does malloc do? Yeah, kind of like the new keyword. It memory allocates. It allocates memory. How much memory are we grabbing? We're grabbing 100 times however big an integer is. So this guy effectively creates me a 100 bucket integer array and returns for me the pointer to that. Make sense? And I'll store that pointer inside of my integer array here. Okay, now we weren't sure last time. I kind of indicated that, at least from old school C programming, because we're in this world right now where we're using a modern C compiler that's going to let you get away from some stuff, get away with some stuff that you wouldn't have been able to get away with, let's call it 30 years ago or something like that. But assuming we did not cast this to an integer pointer, it would come out as a generic void pointer. And as a generic void pointer, when we try to do math with it, like we're doing here, pointer math, it might take the wrong size steps. I actually suspect modern GCC, it would take the correct size steps because it would do the cast for you. But I was explicit here and said, that guy's an integer pointer, so take integer size steps. When we add 1 to it, you're taking the size of int, size of step. Make sense? And that's important because that's not necessarily related to what we're doing here. All malloc does is it gives me a chunk of contiguous memory big enough to hold 100 integers. Now, in a language like Java, we're only allowed to put put integers in there. In C, here's memory. Put in there whatever you want. But I've given you enough to hold 100 integers. So if we say an integer is 32 bits, 4 bytes, so I got 400 bytes of memory. Yeah, you put a 400 byte string in there if you really want to. It doesn't matter. You got 400 bytes of memory in a row. You know, do what you want with it. All right, but we're going to treat this guy as an integer array. Then we went ahead and we spun through and we said AR at bucket I. That's what that guy is doing, right? We're doing some integer math here. So we're saying set the value. So star dot says set the value at this memory location. That is the base address of AR plus an offset of I. First time I is 0, then it's 1, then it's 2. So that's a number of steps of size int walking down the array. Set that equal to some random number between 0 and 100. Okay? And then we went ahead just for testing purposes and we printed out all the numbers there. So I'm printing out as a decimal the value at, that's how we're reading that, the memory address AR plus I. Go ahead.
Question. So if your array is char array, can you do that math?
Sure. You would just take,
But the size of it, like I is an integer, and you're incrementing the size.
I is a number of steps. Think of I in this case as steps. All right, so we're going to use the little squares here. So these squares are byte size squares on the ground, right?
Yeah.
So I'm at AR, I'm at the beginning of the array. In an integer array, if it's 4 bytes, I have to take a 4 byte step. Can I do 4 bytes? That's where the next int is.
Yeah.
Then plus 2, right there. Right? But if I'm dealing with chars, plus 1 is the size of a char. And in C, that would be, it uses ASCII, so that's 8 bits, 1 byte. So that's the size of my step. Plus 2, plus 3, plus 4. That make sense? Yeah, so they think of that plus I thing as how many steps we're taking, and then the type of memory, the type of item we're storing indicates how big that step is. Got it? And that's related to what I was saying a second ago is, you know, we get a plot of land of 400 bytes here because I said, give me 100 times size of int. Presuming size of int is 4 bytes, I got 400 bytes to work with here. I could put whatever I want in those bytes in a language like C and C++. Java is more picky. Java says, look, we're going to police what you try to put in here. But if I really want to take steps of size of char, I can do that. I could say AR plus size of char and take little baby steps and overwrite part of the binary of my integer and get some really wacky results. So if I store an integer which is taking up 4 bytes and I only take a 1 byte step, I'm going to overwrite part of that, the last 3 bytes of that integer with the first 3 bytes of my next integer, which might actually be a pretty decent hashing algorithm. I mean, you're not going back because you are overwriting stuff. Yeah. Well, hashing is one way. It's a one-way cipher. So you don't need to be able to go back. You know, you put arbitrary size input and it spits out a fixed size output that should be unique per input, even though since there's a finite number of outputs and there's infinite size inputs, there are collisions, but they should be rare, let's say. The idea is that by just having something like that where you just have your data destroying some of the value but still giving you a unique output, I mean, it's a reasonable hashing algorithm that should be, you know, probably secure enough for, I don't know, like the online chutes and ladders or something. All right. So, any questions of what's going on here? So this is just proving that we have 100 numbers, right? So I'm going to go ahead and dump a lot of this other stuff. I've already pasted it somewhere, didn't I?
Mm-hmm.
All right. So go ahead and save that. Let's just run this guy real quick. I still have my big money. Did anybody figure out how to make my text bigger down here? All right. So there's 100 random numbers not sorted. So we want to be able to sort that guy. Now, let's go ahead and just move things around a little bit. So I'm going to create a function down here. It's going to be void fill array. And this guy is going to take an int pointer, AR. I will take all my crap from here, paste it in there, just for testing purposes. I'm actually going to copy that. I won't print it in here. I'll print it again back out here, but I'll take the filling out and just print. So we'll go ahead and call fill array. and I'll pass it AR. All right, so I have a function here called fillArray that returns nothing, takes an integer pointer as a parameter. I go ahead and I go through and I fill it up with a bunch of numbers, and then I am done. Come back out here. I go through and I print out all my values. Oh, good. Very happy with that. Remember I introduced prototyping? The default compiler adheres to that. So we can either put that function before this, or the cool kids would do is they would go ahead and prototype it up here. And actually, you don't even have to name the variable. Just go that like that. Now it's happy, right? So I prototyped it. Go ahead and run it, get the same output. So I've done the same logic, but what have I actually done here? I passed in a pointer. This is passed by address, right? We're thinking about it like normal programming. So pass by address, we passed the AR, which holds a memory address. This guy received it. I just happened to store it in another variable called AR. Went ahead and I filled it up here. Ended. Why didn't I have to return the value? Somebody usually doesn't answer. Why didn't I actually have to return my filled array here? As soon as, right after I called it, I was able to use it here and prove I could print the stuff out. Yeah, I passed it by address. So I let this guy know where in memory I wanted it to fill. He went to that place in memory and filled it up. Then I came back here, and after this guy was called, I went through and proved that it filled it up. Make sense? Okay. So with that in mind, now let me actually just show you one other thing just for the sake of completeness here, since it's available to us. I'm going to go ahead and create another file. And we're going to call this guy, I'm going to save it. We're going to call this guy blah.h. Okay? You can name it whatever you want. And I'm going to go ahead and I'm going to go back over to my test.c. I'm going to steal this one line here. And I'm just going to paste it inside of blah.h. And I'll go back over to test.c. I'm going to do include double quote blah.h. Make sense? So you're kind of, what we just did there is the evolution of how C header files were found. We started off by you just write, you might put all your functions before main, but then you start running into an issue of what if this function needs to call this function, then you have a chicken or the egg problem where they don't know about each other. So then the next thing we would do is we would start prototyping all our functions at the top, implementing them at the bottom or sometimes later. That way the single pass compiler could find the symbols. But then what we said, okay, well now the top of our file starts getting too complex, so maybe we just go ahead and put that stuff in a separate file, a header file, and we go ahead and include that header file up there. And that header file effectively has our prototypes in it. That makes sense? That then allows us to look at our header file and effectively see all the stuff that our program is doing at kind of like a bullet point level. So I'm going to go ahead and I'm going to update my header file here. I'm going to say, okay, well, we're going to have a void, what we called it, insertion sort, right? So void insertion sort will take an int pointer as a parameter. So just go ahead and add that to my list to my header file. So that's going to be available to us in here. I'm actually going to steal this just so in case I have a spelling mishap. Even though I've never had a compile error, I have lots of spelling errors. So actually one of the hallmarks of my personality, I guess. Okay, so this guy will take in. Now notice when we actually write it, we do have to name that variable. From a compiler perspective, and this goes down to, what's polymorphism again?
Same method with different, or same method name with different inputs.
Number and or type of inputs. So if I had two different, in this case, functions, one that took an int pointer AR and another that took an int pointer cat, Are they the same function? They are. Programming languages don't care what the name of your parameters are. When you write it, you have to implement it in terms of what you named your parameter. But if you have two functions that have the exact same name, the exact same return type, and have the same type and number of parameters, they're the same function. That's why here in the header file, I didn't have to I mean, it wouldn't have been wrong for me to say the name of the parameters, but I didn't have to specify the name of the parameter I was going to use. Because all the compiler cared about is, here's a function that's going to take an integer pointer. Make sense? All right. So we're seeing in some of these older languages some evidence of things from the that we see in the future. All right. So insertion sort. We're going to have our integer array. We typically start at bucket 1, and then I usually have that variable called the follower. You remember? And I usually make the skull. You've been in that class? That's new since I got my emoji thing. I hate all of you. What's up?
Added value.
It is added value. It's the only thing that thing's worth. I always get upset when I don't get good suggested emojis. All right, so we're going to go ahead. We're going to create an int follower. And we're going to have a int. Let's go. We'll stick with I just because that's what the cool kids do. So we'll say for I is equal to 1. We'll start at bucket 1. I is less than So now we have a little bit of an issue. I need to know what the length of that array is. I can't ask the array for his length, can I? They don't have that. So we could pass the length in here. So maybe we say, okay, this guy is going to take in as well as the length. So then I is less than length. I plus plus. All right, so this is going to start at bucket 1, go all the way to and including the last legal bucket of my integer array. And then when we're in there, we're going to try to bubble that guy towards the top as far as he goes, which is why I think this should be called bubble sort, but it's not, so whatever. All right, so inside here, we're going to initially set follower equal to the current value of I, right? Because that's potentially what the guy is going to do. Then we want to possibly swap as we go up. So while I is greater than 0. So we're not at the beginning of the list. So we potentially have somebody to swap with. And then we want to say the value at, and we're going to write this the cool kid way, right? Using pointers, not stupid array syntax. Nobody likes array syntax. It just makes you, All right. So
If we're using array syntax, we could take the length, though.
well, no. I mean, C supports. That's actually an interesting question. That would have not worked before. Can you take I don't know, can you take the size of AR? Will it give you 100? Did you test it?
Well, I think if we had it as an array instead of like.
It is an array.
But we're passing it as a pointer. If we were passing it as an array instead. Oh, well.
It should be the
At
same.
that point, it becomes a pointer. But if you define an array in here, what I realized is you could take the size of them and divide it by the size of int.
Okay.
So because it's
Yeah,
you get the size.
that's a more modern thing.
Yeah.
Yeah, that's cool kids wouldn't do that. Is that one of those flavored Diet Cokes?
Just got this right.
Oh, it's just a new can? Have we had any of the flavored ones yet? Like the mango or?
Only one I want to try is the blood orange.
I heard that one's the best.
So, all right. So y is greater than 0. What was I talking about? Oh, then we're saying as long as we're not at the beginning of the list and we're supposed to swap. That's the secondary question, right? And how do we know we're supposed to swap? If the current guy is less than the previous guy. All right. So the current guy is the value at AR plus this is going to get ugly, I guess, because we need to have the well, actually, we can say plus follower. Yeah, this will work. The value at AR plus follower. which will give me the current position. If that guy is less than the value at AR plus follower minus 1. If the current guy should come before the guy before him. Make sense? If that's true, then what are we going to do? We need to swap. So I'm going to give myself like a temporary variable to do the swap. So I'll say temp is equal to the value at AR plus follower. Then we'll say AR plus follower. That memory address, actually, no, we want to say this. That guy is equal to the value at AR plus follower minus 1. And then AR plus follower minus 1 is equal to temp. So we'll do the swap. And actually, this will boil down to a memory address. Should be this. All right, so that'll do the swap. Then what are we doing? Then we're going to say follower follows. So we're going to keep doing that until we either hit the top of the list, top of the array, or we should no longer swap. When we fall out of there, we spin back up. I becomes the next version of I. Follower resets. We do the same thing again. We keep doing that until we run out of stuff to check. All right. Now, I'm also going to go ahead and I'm going to create a print array just so we can conveniently do that. So we're going to say print array, and this guy will take in an integer pointer. Go back to test.c here. And print array also needs to take in an int length. So realistically speaking, the fill array thing also needed to take in an int length if we want to be complete here. And then we'll say less than length. I is less than length. Misspelled it. I plus plus, and we'll say printf %d \n, the value at AR plus I, and then we can kick it down one last line right there. So that's my print array. So we want to fill the array, then print the array, then call insertion sort, then print the array again. And maybe just to keep things separated a little bit, I'm going to go ahead and do a printf. We'll just do some asterisks here. Then I'll steal that same number of asterisks. And we'll plop it right here. That way we have kind of borders around our prints. Come back up here. We call fill array. And this guy's going to take in the length. This is 100. Maybe we want to go ahead and, well, there's a define thing, but I'll just do it here. So I'm going to say length is equal to 100. We'll use length there. Then we can use the length right here. Then we'll call print array, passing it AR and passing it length. Then we'll call insertion sort, passing it AR, passing it length. Then we'll call print array, passing it AR, passing it length. Oh, couple of problems with my header file here. These guys now take int length, actually just ints. All right, so there is my sorted array. And there's my unsorted array. Look pretty good. All right, so that's a reasonable version of the homework assignment. If you didn't put things into functions, that's fine. I kind of maybe assumed you would have done it all in main, at least initially, as you're just getting used to main, or you used to C, but we kind of get the function thing and how prototyping works and how putting in a header file might be beneficial, blah, blah, blah. Go ahead.
I have a question. So with this, sorry, this is kind of, but with the rand function, for some reason, well, I know why it's not. So it's not seeded.
Right. So is it always giving the same values?
Why isn't it seeded?
That's actually a good question. I think it typically. This actually goes into another topic in computer science, which is what is a good source of randomness. So typically, there's another function called srand that you can use that allows you to seed one, and typically what you do is you seed it off the milliseconds on the current time. So you seed it, because srand allows you to give it a seed value, but then the question is, well, what should the seed value be?
Yeah, I was curious why I was getting the same sequence. So
Yeah,
I saw that by default it's seeded by one.
that was pretty common for a long time. Java's random number generator used to do the same sequence as well, and now I think it pulls from most Unix operating systems have a or Linux rather have a Etsy garbage, have basically a dump file that has just random gibberish in it, and you could just use that as your seed value, and then it just kind of magically gives you pseudo random numbers. Any of these would be considered pseudo random numbers. It's actually an interesting area of computer science, was what is a true source of randomness. It's difficult to find. Some people, like, you just move your mouse around a whole bunch of times, that generates data, but even then, humans, because of the way we work, there's patterns in that and stuff like that. But really, it's that original rand is just a simple random number generator, and it just operates off a basic starting point, and because it's always the same starting point, it always gives you the same number. Which is okay for testing, but if you want to have a program that's going to give you, like random, like guess a number, well, the number will always be the same number if you use rand. But if you use srand with the current system time and it uses the milliseconds off of it, then you get, from a human's perspective, pretty good randomness. All right, so let me give you this guy as a starting point. Oh, how?
Go all the way to the top right.
This guy?
Yep, wheel. And kind of collapse this one.
Collapse this one?
Yeah.
That is, he doesn't collapse. Did I scroll down?
Okay, yeah, go use the settings in terminal. Down a little bit. And then you'll see the slide.
Perfect. Is that good? Bigger, smaller? Perfect? All right. Thank you. I told you I'd figure that out. Okay. So, I was going to put this on Slack. I'm not going to put the header file up there. Can we handle it? Put the header file? You can prototype the functions if you want. Okay, so now we want to mess around with some strings, and also reading stuff in from the user. So let's go ahead and dump all this. Okay, and well, I'll leave blah.h up there for right now. I won't fill it with anything yet, but we might put some stuff in there. And I'll also just leave it with standard IO, although actually we're going to be using malloc here pretty quick, so I'll leave the standard lib up there so we have the standard library stuff. All right, so if we want to read a string in, okay, now again, if we're gonna create a, how do we represent a string? If we want a string that can hold up to 50 characters, we would use malloc to go ahead and create that. Or we can be the uncool kid and do the char array 50 thing. We don't want that. So we're going to say, so what kind of value is it going to live in? It's going to live in a char pointer. So we're going to create a char pointer, maybe called s, and this guy will be equal to the char pointer version of malloc. And we'll say 50 times size of char, something like that. Okay, now we saw last time, I think we can say something like s is equal to hello, and then we can say printf %s \n, and that will print out hello. So there's my hello. And we know that following the, so this is bucket 0 through 4, right? So the next buckets up to 50 is going to be filled with what? What value will be in those buckets? \0. That's the string termination symbol. \0. All right, so if at some point I asked you on a quiz what the string termination symbol is, you would say, it's that guy. String termination symbol. Got it? All right, it's going to be an important thing for us because sometimes we might need to search for that guy to find out where the end of a string is if we're doing some manipulation stuff like we might be doing in our homework assignment. You know, hint, hint. So we've printed out s here. All right, well now it'd be nice to be able to, instead of just having s equal hello, it'd be nice to read something into s, right? So the user can have some interaction here. So we're going to go ahead, we're going to do a printf, enter a string. All right, and I'll put a little space after that. Now, this is not going to kick it down a line, so it's going to say enter a string and be sitting there. But now we need to block so that the user can enter something in. Okay? So what we're going to do here is we're going to use a function called scanf. And let me just do something down here. So if you want to know how a function works, just do man. Man stands for manual page. Scanf brings this guy up. You see there's ones for file and things like that. But so scanf takes something pretty similar to our formatted string for printf. So it's the things that we want to read in. And I think, doesn't the book talk about scanf as well?
Yeah.
So let's look at that in the book. Because we're going to be reading in a %s into s. Well, we'd probably read something in here, right? Yeah, so here's an example of scanf. So we're reading in a %s into a memory address. First name here, even though they've written it the uncool way, this is the non-malloc version of that. You see how ugly and simple that looks? I mean, if we're going to program in C, we should feel like we're programming, right? Otherwise, we might as well use a modern language like Java or C#. We want to get to we want to use our computer.
I don't know. From one standpoint though, it's almost more useful to have it like that right now.
Oh, absolutely, we better have it that way. I mean, the reason I'm kind of forcing the issue of using the pointers is because when we start really working with system calls, having that kind of we need to practice with pointer math right now. That's going to be very beneficial to us.
As soon as something is passed to another method, it becomes a pointer anyways, right?
Well, not necessarily.
No? Okay.
No, I mean, like for instance, if I have an integer I and I pass I to another function, I'm passing it by value. If I want to pass the address of I say ampersand I. Then I'll have the address.
The reason why I'm asking is because, like I was saying earlier, like, so if I take an array that I define it as an array like that, and I pass it to another method, it's now a pointer.
Well, it's a pointer anyways.
Yeah.
Yeah, I mean, at the end of the day,
Stuff on it.
at the end of the day, first name one here, its value will equal the same thing, or it might be a different memory location, but the same thing as saying char pointer first name is equal to malloc 50 times size of char.
I just can't treat it like
Because of the way it's built in the current version of GCC, more modern compiler. That would not have worked historically. So they're kind of making it a little more friendly. That's why, I mean, you actually see it. See, look, they're actually cheating here. They're just passing in a void for main, where what I've shown you here for main is you're taking in an argument count as well as, so what kind of animal is that guy? A char pointer is an array of char pointers where each element of the array is a char pointer. So it's an array of strings. Make sense? But if you go back and look at any old school C program, you'll see it written like this. Because you need to know how many of these guys there are. Because he won't be able to tell you himself. Does that make sense? So those other tools are things that have been added to the language in more modern versions.
I'm just saying I wish I could do size of that.
Yeah, but convenience is for wimps. Right, Annie? No, we don't want convenience. We want to have scary pointer math. All right, so in any case, we're going to go ahead and we're going to read something in. So we're going to scanf. We're going to be reading in a string, %s. And we want to read that into a memory location. S holds a memory location for us, right? Because S is a pointer. Pointers are built for holding memory locations. All right. So I'll go ahead and run this guy. Enter a string. We'll say Mike. Oh, yeah. Don't set it back to. Like, look, whatever you just read in, I'm undoing that. Did exactly what we told it to do. All right, there we go. All right. I misspelled it, but misspelling it all, I came through. Okay. So now, we've worked with manipulating strings, right? In Java, those are always fun things like reverse a string. And for instance, we might want to have some convenience functions for us that we are used to using with Java. So for example, we might want a function index of that takes a char pointer. We'll call it S, so it acts like it looks like our string. Probably also needs to take in a length, and then takes in a char C, the guy we're looking for. So this guy returns the first occurrence. Is that spelled right?
No, that's right. No, one R.
First occurrence of C in S, or returns the position of the first occurrence in C, or -1 if not found. All right, so that's our equivalent to Java's index of. All right, then we probably want to have a char at, takes a char pointer s, takes an int length, and this guy returns the char that lives at position index in S. Then we probably want to have a, now we can do a couple of things here. If you had an ability to reverse a string, would you want the string to be reversed permanently, or would you want a reversed version of that string? Yeah, see, I agree. We should probably have both. So, all right, so we have reverse string, and this guy's going to take in a string, its length. The who? Oh, there we go. And this guy returns a new string that is the reverse of S. Then I'm going to steal this, and we're going to have a version of this that returns nothing. And this guy reverses S in place, which means we reverse it in its current memory position. So from that point forward, it's going to be reversed. Make sense? All right, then to bring it all together. Well, this is too easy so far, right?
It keeps going.
Oh, you don't want more than this? We only have 4 functions. We do one more. Or two more? 3 more?
Wait, the last function has the same name as before.
Yeah, but it has a different return type.
So we can have that?
That's a good question in current GCC.
I'm not complaining.
There, I have to put main. Actually, I never call it, so that should be okay. Yeah, conflicting types. All right. Yeah, so it's the number, but it didn't catch the type. So those were the same. So we would have had to, what we probably would have done is maybe taken a Boolean here, whether or not it should be done in place or not, but we'll just write it this way. This is fine. All right, so then the last function is going to be called, this is going to be char pointer, remove vowels. I'm going to take a char pointer as a parameter and int length, and this guy returns a new string, which is the original with all vowels removed. Make sense? All right, so homework for Friday is write all those functions. I'll put this up on Slack. I'll put the assignment up on what's it called? Blackboard. All right. I will see everybody on Friday.